Good morning, students. Your physics teacher Hassan Darwish with you. In a series of videos, I'm going to explain Chapter 2, the linear momentum. Now in this video, I'll explain the concept of the linear momentum of a particle. So let's start. Now in this objective, define the linear momentum of for a particle, as I said. Okay, concept and definition of linear momentum. Let's have a look at this picture. Now in this picture, an accident is about to occur. We have an 18-wheeler truck and a mini copper car, and they would enter into a head-on collision. I mean face-to-face collision. In your opinion, which way the damage will go? To the 18-wheeler truck or to the mini copper car? So we can conclude from your answer that the effect on motion, or the effect of motion, or the amount of motion depends on the mass, right? The bigger the mass, the bigger the effect. I mean, the bigger the amount of motion. Okay, so motion depends on mass, right? Let's have a look at another example, another situation. Can you stop with your hand a light bullet? I mean here by light bullet, very small mass. Means mass of the bullet very small and even negligible. Moving with the high velocity? Of course you cannot, right? It means that also the effect of motion and the amount of motion depends on the velocity. So from the two examples, or from the two situations here, we conclude that the effect of motion, or the quantity of motion, if you can call it, depends on mass and velocity, right? So this quantity, which depends on mass and velocity, is called what? Linear momentum, or let me call it simply momentum of the particle or of the body. That's the concept. Now, how do we obtain the rule of the linear momentum? You remember Newton's second law last year and the year before for a particle. The resultant force Fr means resultant force acting on a particle. Here it is, resultant means sum of forces acting on a particle is equal to the mass of the particle times the acceleration, right? But what is the acceleration? You remember? Acceleration represents the time derivative of velocity. It means derivative of velocity with respect to time. That's the meaning of prime. So d over dt means prime, okay? But here we emphasize on the time derivative. That's why we write over dt. So if you replace it here, you get what? Resultant force, or sum of forces, is the derivative, which is here. Here is this is called derivative. And we mean by this derivative prime. Okay? It is the derivative of the quantity, mv. Let me write it in the form you know. mv, you see this is vector quantity. And here is the prime. Clear? Here is the prime. So the resultant force is the derivative of the quantity mass times velocity. Here it is. Mass and velocity. So this quantity which is equal to mv, is called, this quantity, which is the mv, is called the linear momentum of the particle. Okay? So what is the linear momentum of a particle? Linear momentum, P equal mv. So it's the quantity of motion which depends on mass of the body and its velocity. Okay? But you know that mass here in the school is always constant and positive. This means that the two vectors P and V have the same direction. Any problem? Now you remember, or don't forget, this is a vector quantity. So the magnitude is P equal mv. In mathematics, you may write it in this way. That's the magnitude of the vector in math. You write it in this notation. The same, okay? Magnitude of P is equal mass of the body times the magnitude of the velocity. Okay? Now what's the SI unit of P? This is mass in kilogram, speed meter per second. You get P in kilogram meter per second. And so you can write Newton's second law here and write it in this form. Resultant force, or sum of force, is the same. Sum of forces represent what? The derivative of the linear momentum. Okay? That's Newton's second law in terms of momentum. Okay, let's do a direct application. Example. In this example, we have a car of mass 800 kilogram moving on a straight and level road. At t equal to 0, the driver fully applied the brakes. Fully. It means what? When you fully apply the brake, means you press with your leg or with your foot on the brake pad. You remove it from the engine pad, right? So this means that when you fully apply the brakes, no more engine force. Be careful about this. The figure below shows the graph of the variation of linear momentum of the car during the braking time, or the time of applying the braking force. You see here it is a straight line of negative slope. The resistance due to air to the forward motion of the car is assumed constant. It is 400 Newton. That's due to air. Calculate the initial speed of the car. Okay, let me take a new page here, white page. So part A, initial speed means at the instant t equal to 0. At the instant t equal to 0. Okay, here is the time and here is a 0 time. We have what here? Linear momentum, not velocity. So that's the initial linear momentum. So I can say at this instant, magnitude of the linear momentum P without a vector, or you can write it in this way. Magnitude, which is always positive number. Be careful. The magnitude is always a positive number. That's why in mathematics use this notation for writing. Here at t equal to 0 means I need the initial linear momentum. So the initial velocity. Mass is always constant and positive. Just replace the numbers. So let me write it now, the speed in this form. Initial linear momentum 20,000 kilogram meter per second, right? and the mass of the car is 800. Here it is. 20 thousandths and the mass is 800. If you do the calculation, you get 25 meter per second. Okay, any problem? Good, so very simple job. Part B. Name and represent the forces acting on the car. Okay, here's my car, don't forget. Moving on x-axis. So here, let me use a vector. This is x prime x, okay? And here is my car, say, which can be represented by the particle model. Now, what are the forces acting on the car during motion? It's weight, right? Normal reaction of support upward. Air resistance, don't forget air resistance. It is assumed constant. And the braking force here, I'll displace it a little bit to see the two factors. Here is the friction force. So this is x prime x. And the forces are the weight, W, the normal reaction of the rod of support. This is the sense of motion, don't forget, which is represented by the velocity vector. Be careful, V is not a force, okay? So this is air resistance, let me call it F air, FA, for air resistance. And this is the friction force, F. Okay, any problem? You have to name them in the exam. You have to name the forces. But here I do not have enough time to name them. Part C. Determine the magnitude of the force of friction between the wheels and the road. You know, from the last year and the year before that, when there is motion and forces, and you want to calculate acceleration or a force, you must remember Newton's second law. Clear? We've just studied Newton's second law, that resultant force or sum of forces acting on the body is equal to ma, right? Or the derivative of the linear momentum, the same. But I'm going to use this form of the Newton's second law, which is the linear momentum, Newton's second law in terms of momentum. I can also write dp by dt as derivative p prime. You know this from mathematics. Okay? Or equal ma. But I prefer in this example this notation. Why, in your opinion? Why I use this notation? Just simply because I have here the graph of linear momentum and I'm going to use this graph. Okay? So replace here the forces. We have W plus N plus friction plus air resistance. Okay? Equal P prime. But since the motion takes place on x-axis, the weight and the normal cancel each other. And we can say directly that minus friction. Why minus friction? Without a vector, you cannot replace numbers here. Be careful, because this is a vector equation. Minus F air equal, sorry, or nothing, equal P prime, which is a derivative of P, Okay?